minutes of slides maybe, and then it's really just a jumping off point to start some conversation. Okay, great. So I'm going to talk today about HEIR and what HEIR can do as a platform for researchers who want to get involved. I'll start by a quick introduction for the recording. So I'm Jeremy Kuhn. I got my math PhD at the University of Illinois at Chicago, currently based in Portland, Oregon. And on the personal side, I've been writing math books and math blogging for like almost 15 years. So I'd love to do that on the side. But in my professional life, I'm staff engineer at Google. Our team is the Phazon team, and that's the team devoted to homomorphic encryption. I'm the technical lead for the HEIR compiler, and our goal really is to bring FHE to production systems at Google and hopefully through HEIR's open sourceness to the rest of the world. So quick agenda, I'm going to give a one-slide pitch for the HEIR project. I'll talk about sort of my perspective of where industry is at currently. I'll talk about the research potential of HEIR at a high level, and then dive into some of the details of HEIR's design and what makes it very nice to work with. So here's the one-slide pitch. So we are building a compiler toolchain. This compiler toolchain is built with the MLIR framework. With all of the established ideas in FHE. So we want to have every FHE scheme supported. We want to have fast polynomial math. We want to have all of the nice optimizations that researchers come up with. We want to have noise models, parameter selection, everything to accelerate FHE research so that researchers, you can focus on implementing your novel idea and not on rebuilding compiler infrastructure from scratch every time you want to do a new project. And we want to lower the barrier to building production homomorphic encryption projects. So we will have benchmarking, we will have lots of hardware targets, front ends, everything that will make it easy to actually use FHE in the real world. If that's enough for you, you can leave the call and join our working group. So we have a website and our GitHub project, and here's just a quick list of a bunch of the universities and startups and big companies that we're working with. I won't go over there, but there's a link to our meeting calendar if you want to join us more regularly. Okay, so moving on to where is industry at currently. This is going to be something of a biased view from my perspective, but I have a pet project where I hunt around the internet for people who are claiming to use FHE in production, and I try to come up with a publicly verifiable way to prove that they are actually doing what they say they're doing. So I have this blog post I'm maintaining where I have all these examples, but some of the nice ones are that recently came out where this like Apple has been deploying a bunch of stuff around private nearest neighbor image search and caller ID lookup, and Google has this thing called private joining compute, which uses a little bit of FHE, and the very first one I think was Microsoft's password checkup, which as far as I can tell is still in production. But in all of these production deployments, HE is mainly a small component of a larger privacy protocol, and these privacy protocols are handcrafted for the application at hand. And so we're interested in sort of going beyond this to have some more general purpose HE applications. And what are the incentives from the industry side? So for one, we have the European Commission and to some extent the United States that is increasing regulatory pressure on big companies to be better with user privacy. We have a lot of products that could use it. So this is a icon explosion of all of Google's random enterprise products that like we've talked to people from each of these teams that think they could have some use for homomorphic encryption if only it was fast enough. And at Google, at least, all of the people who are coming to me who want to try to use homomorphic encryption aren't doing it because the individual engineers who are interested in it aren't interested in it for any reason except they think it's the right thing to do. So they want to do something with some user data. They know it's kind of creepy or a privacy violation, and they're like, okay, how can we avoid that and do the right thing? But on the other side, there are some big barriers. Mainly, FHE is hard to use if you're not an expert, and there is quite a large performance overhead still. So of course, the solution, I think, as many of you know, is to come up with some hardware accelerators that we can deploy at scale. So here is a list of a bunch of acronyms that are all, as far as I know, hardware accelerator or research projects. The ones on the left side I've heard of. The ones on the right side I just learned about last night when I was going through the list of all of the hardware accelerators out there. So there are quite a lot. And it should be noted that like the many of the companies that are working on this in the private sector are taping out chips now. Like I've had multiple promises from different companies that I will have a board in my hands next year at some point, maybe mid-year. And many of the FPGA projects are ready now, right? Like you can already use them, and we're already doing integrations with them. So why do we need FHE compilers? This is a slide that I wrote in 2022 when I was first launching the project. We have lots of legacy application code that we don't want to rewrite. We'd rather just recompile it. We have crypto expertise, but it won't scale to huge organizations. We have trade-offs, lots of trade-offs in FHE that need to be machine assisted. And we have lots of abstractions to manage when you take the cross product of all the different FHE schemes, performance tricks, and possible hardware targets. But I'm going to be a little bit facetious and say this is like not the real reason. The real reason is that we need to figure out what's going to go here. So we want to scale up FHE over the next 5 years, but we don't know what is going to be the right solution for production workloads. And so the compiler is a tool for us to target all of the hardware backends, do proper apples to apples comparisons, and figure out what's the cost effective thing for industry to put to make a financial bet on. Okay, so let's move on. That's sort of the industry side of things, where we're coming from. And then now the question is, where can researchers get involved and what's the benefit for them? So the short recipe that I'm pitching to you here is that if you have a new idea for some FHE innovation, you can start by implementing it in HEIR, and you will get a bunch of free stuff. So you will get the rest of the compiler. You will get front ends and hardware and software backends to test against. You will get a whole variety of testing tools and debugging tools that are already there for free. And you will get basically me and Asra and Alex and people who are really invested in this project, willing to help train you on anything that you're not familiar with the project, to help you implement things, to give you code review, and to give you, assistance with ideas for how to do things. And as a result of all of this, you will hopefully be able to publish your ideas faster than you would if you were writing a compiler from scratch. Some of the big, there are a lot of big research questions. I think that the compiler sort of enables that are hard to do in a different setting. So I think most of FHE software implementations make a bunch of program agnostic performance assumptions. They always assume you're going to do an RNS representation with a certain number of limbs and a certain bit width, or they're always assuming you're going to be doing CGGI ciphertexts in with 4 bits or whatever, and you have some knobs that you can tune, but you tune them manually, and then the libraries just assume everything. So one of the big questions is like, what can we gain from having a global view of the program in order to make those decisions with knowledge of the program that's being compiled? There are some research papers that have started to answer this question in small ways. As far as I know, they have all built their own compiler to do so. But we're hoping that we can answer this question a lot more comprehensively. There are also things like, of all of the competing optimizations, every paper that publishes an optimization claims that it is 5 times better than the state of the art. That can't all simultaneously be true. So there has to be some optimization choices that end up being better than others, and we don't have like a good way to figure out which ones are the dominant ones. Even if you make an assumption about certain types of workloads. Then there are all these questions about how we should do packing and how we should lay out data across ciphertexts. Another question that has been coming up for me recently is, what's the best order in which to optimize all of the choices we need to choose? So you have packing choices, you have RNS representational choices, you have choices about which program tricks to implement, and it's not clear to what order. You have to pick some order in which to optimize these in the compiler, and you can have a lot of interesting questions around reorganizing the order in which you choose things and refining things in different ways. Scheme switching is something that is on our long-term agenda. We'd like to have scheme switching support in the compiler, and then there's a bunch of questions around how do you program how do you partition your program into sections that are better for SIMD FHE versus Boolean style FHE? How do you do noise analysis across the different schemes? And then, of course, what sort of cost models will help us navigate all of the different performance tricks that we have available. So this is just a sample of some questions. And then there's like more basic questions. Like some researcher came to me and he's like, I have an idea for like a better implementation of BGV that I could just like make a backend for, and could we plug HEIR into that? And I said, of course, that would be awesome. So there's lots of areas that you can get involved. Okay, so I'm going to dive. I mean, if anyone has any questions at this point, I think now is a good time to pop in and ask some questions. Otherwise, I'll move on to some of the nittier grittier aspects of HEIR's sort of internal design. Okay. So HEIR is built on top of this MLIR compiler toolchain. So this was originally, so it was created started in 2017, I believe, or 2018 maybe. At least internally at Google, it was started then. And the goal was basically the guy who invented LLVM, I'm blanking on his name right now, he got hired by Google to work on machine learning stuff, and he looked at all of the TensorFlow nonsense that was happening, and he said, this is a compiler problem. Why don't we have a compiler for TensorFlow? And so he built MLIR as a way to allow TensorFlow to have high-level tensor style optimizations. And then he said, okay, well, as long as we're building a new compiler toolchain from scratch, why don't we make it a generic compiler toolchain that can be the compiler toolchain to end all compiler toolchains? I don't know if that necessarily happened, but it did unify the TensorFlow ecosystem at Google. Now all of that stuff runs on top of MLIR. And there are dozens of successful compilers that are built on top of it. And it comes with batteries included. So there are generic optimization passes like constraint or common subexpression elimination and dead code elimination and inlining and that stuff, which can be applied to any of the compilers built on top of this toolchain. And it has multiple backend targets like LLVM, and there's a couple for GPU and other OpenMP style things. So it's MLIR is not just part of Google, it's really part of the LLVM Foundation, and it lives in the LLVM project upstream. So this is something that people are working on from across the industry, not just Googlers. Yes, okay, I think I basically said all this stuff on this slide already, but yeah, okay. 4 pictures for repeating what I just said. So internally, the way that MLIR works is it has sort of an internal representation that corresponds to like generic operations with operands and results and types. But then when you're using MLIR, you can define these things called dialects, which are sort of an instantiation of these generic operations with particular names and particular types and particular constraints on those types, where you're supposed to impose semantics on top of that. So there's, for example, an arithmetic dialect, which handles arithmetic types, arithmetic operations, like addition, subtraction, multiplication, comparisons. But there's also another dialect that handles sort of tensor operations, like if you're going to insert and extract from tensors, or if you're going to, there's another one for linear algebra, one for memory references, one for all kinds of things. And so the idea is that anybody can build their own dialect on top of MLIR. It plugs into the system. And the idea is that all of these different dialects, they're kind of like different intermediate representations in like a traditional compiler, but they can all coexist in the same program. And the compiler passes that you operate on have to make sort of assumptions about what types of dialects show up, or else handle things in a generic way. So in HEIR, we have this sort of evolving structure diagram that describes the different dialects that we have built at different layers of abstraction at which we do. This is kind of the main idea of MLIR, is that you define a dialect at a particular layer of abstraction that makes it easy for you to write the optimization pass at that layer. And so we have sort of scheme-specific dialects that would allow us to write optimizations that are specific to BGV at that layer, and they would know everything that BGV needs to know at that point, rather than doing it at like the lower level of polynomial math or the higher level of just like generic program data flow. So I've sort of grouped this into 3 rough levels. It's not like a hard and fast divide, but this is roughly how we do it. At the top, we have the input languages, like we have some support for input from machine learning frameworks, like you take a compiled TensorFlow model and to some extent you can get it into our system. I'm currently working on a Python front end, and I have hoped to have a C++ front end in the future. But these get abstracted, these get ingested into a sort of generic model of private computation. So I'll go into this in a bit more detail, but the idea is that you basically annotate which data types are secret, and it will do a data flow to tell you which intermediate values in the program are secret. And then you can have various FHEs, scheme agnostic, but still FHE aware optimization passes. Like you can do a packing analysis, and we have a dialect called tensor extension dialect, which has things like it models the what do you call it? The SIMD model of RLWE, where you can like do rotations and various types of permutations. So it models at that level, and then we have ported some optimizations from other compilers into that model. We also have a management dialect, which represents like a first pass of parameter selection, at least the minimum that you need to do in order to lower to a scheme-specific dialect where you start to instantiate parameters at that level. And then you could do a lower level optimization that does like a further refinement of the parameters. So once basically at that point, we then have to pick, this is also the level at which we would do sort of like a scheme switching analysis to figure out which subsets of the program would be ready for what scheme. Then we lower to a particular scheme dialects. And then we have this dialect called LWE, which is a scheme, the common representation of ciphertexts across all the different schemes. So it handles LWE and RLWE ciphertexts and operations like addition, scalar multiplication, that sort of thing, things that are not specific to the scheme. From that point, our main exit point at this point is to start from these scheme dialects. We will generate code, output API calls against particular software backends, because that is what most of the hardware accelerators use as their entry point. So for example, OpenFHE is an intermediary for Niobium's accelerator. So we generate OpenFHE code, then Niobium has a toolchain that starts from OpenFHE API calls and will generate code for their compiler or for their hardware. The FPGA that Wouter is working on in this call is similar, but it goes through TFHE Rust. And I think we have some other ones that I don't think we've announced yet. But the idea is that you can either now run the results of these compiler optimizations in software using the batteries of these libraries. You can lower them to hardware and run them on the accelerator. And then, sorry, what else was I going to say here? Okay, I think I have more to say about this on a different slide, but the alternative path is then to actually implement the crypto in the compiler and lower the scheme operations down to sort of scheme unaware polynomial number crunching. So we have a polynomial dialect that represents generic polynomial over a modular ring. We have a modular arithmetic dialect that represents the actual individual operations on the coefficients, and we have an RNS dialect that represents the RNS limbs of the SIMD style RNS limbs of the different vectors. Sorry, it's a little bit early for me here. From here, we also we would like to, from this level, generate code against different ISAs. So there's like various people who are working on polynomial ISAs for their hardware accelerators, and this is the level at which we would code gen for that once that's ready. Another thing you can do is you can just take this and lower it down through the normal compiler toolchain down to standard MLIR and down to LLVM, and then you could just run it on x86 or GPU or whatever you want. So this is also something that we're exploring, but that exporting to code libraries is mostly where we're at right now. But you can see at each level you have different optimizations that you can do. Okay. So I'm going to talk a little bit more about some of these layers. So this is sort of what some MLIR looks like in the secret world. So you have sort of an operation which wraps some computation that says, hey, within the context of this computation, this particular value, the condition here is secret, and everything else is clear text. And so the compiler will then use that to figure out, okay, thread it through and figure out which values are actually secret and which values are not secret. And then from there, you can do further analysis. Yeah, okay, I said this already on the previous slide, but we do some heuristic rotation analysis for RLWE schemes. We do high-level ciphertext management, operation insertion, and passes. And then on the CGGI side, we do, this is the stage at which we convert the program to like a Boolean or short int circuit using circuit synthesis techniques. And then we do optimizations at that level of the circuit before lowering to a scheme-specific dialect. Down at the scheme dialects, yeah, so I mentioned we have this LWE toolbox dialect that is the common representation of RLWE and LWE across the different schemes. And then in the scheme dialects, we have scheme-specific ops like relinearization, modulus switching, programmable bootstrapping. And so these are all of the things that differ across the schemes. This is the stage at which we can do noise analysis and reorder the program so as to like insert bootstrapping or relinearization optimizations or operations, do sort of like lazy, relin, that sort of thing at this level. And then down at the polynomial arithmetic level, we have sort of full support for representing polynomial arithmetic. So like we have actually encoded into the, is this? Okay. Yeah, we have coded into the IR the concept of a polynomial modulus and a polynomial ring with like a coefficient type that can either come from, it can either be integer coefficients, floating point coefficients, modular arithmetic coefficients, RNS coefficients of some number of limbs. And then we have a bunch of operations that are happening at the polynomial level, notably the polynomial operation, which we have some minor optimization passes around and an implementation of like a gentleman sandy butterfly lowering to LLVM. Okay. Now at the hardware dialects, this is kind of, I think, the most interesting thing for me, right? So we said, as I said earlier, most of our planned hardware integration is through code-gen to software APIs. And so here's sort of like a short list of the things that we're either working on or planning to work on in the near future. So through OpenFHE, we have integrations with Niobium and Intel's, we don't have them, we want them, integrations with Niobium and Intel's accelerator, which we're hoping to work on early next year. Right now, we currently have an integration with the FPGA, the Belfort FPGA out of KU Leuven through TFHE Rust. And we're working on we have platform-specific dialects, one for Optalysis's optical accelerator, which goes through a C API, and one through TPU, which goes through a library called Jacksite that I wrote that has a Python API. And then many of the teams that we've talked to, going through the software library is the starting point. And they've kind of tentatively agreed that we would like to bypass that software layer and have the compiler basically lower down to the level that's appropriate for their ISA, do sort of static scheduling and data layouts and stuff inside the HEIR compiler, or at least generate a form that they can directly understand in their compiler toolchain, and sort of upstream some of that. So that is a sort of a long-term plan simplification, but my point here is that it enables a lot more optimizations that can happen at that low hardware level for people who are actually interested in the hardware design. Okay, so that is sort of the end of the design discussion. And so some of the researchers I've talked to who have tried to get involved in this say, we've tried to use MLIR, but the learning curve is very steep, and so instead we just built our own compiler and made something custom, and then published our research paper and never used the compiler again. So I wrote this kind of tongue-in-cheek diagram that's people who can read crypto papers and people who can implement MLIR passes, and there's a small overlap. I think based on the number of people who have started working on the HEIR project in the last year, I think that this diagram could be moved with a bigger intersection, because when faced with this, I realized that I need to teach people about how to use MLIR. So I wrote yeah, 13. I think there's even more that are not in this list. Tutorials on how to use MLIR for people who have never used MLIR before and are not like in the compiler. Well, they're in the compiler world, but they've never done MLIR. Or even people who aren't really into the compilers, because I was not a huge compiler person before I started working on this project. I taught everything for myself. But my point is that like I am basically willing to sit down and teach everybody who's interested how to use MLIR and how to integrate things into our project. And I have a bunch of reading material. And so people have started showing up to HEIR meetings saying, oh, I read the tutorials and I have a pass I want to implement. And then we're straight to the question about like what specifically needs to be done to make it work in the HEIR project, which is a much easier conversation than like, you know, what the hell is a dialect? So this is a resource that you can use. And then if you have more things you want to learn about, just ask me and I'll write another tutorial. It's something I've been doing a lot. But yeah, so I will stop here sort of for questions, and I think I'll leave it on this slide here, the design diagram. And I think maybe it would be good to stop the recording at this point, Asra, and then we can have questions off the record.